When graphing a rational function, sometimes our functions are going to have oblique asymptotes. An oblique asymptote might also be referred to as a slant asymptote. They are not vertical or horizontal. A rational function will have an oblique asymptote when the degree of the top is bigger than the degree of the bottom. And if the degree of the top is bigger than the degree of the bottom, what we'll have is an improper rational function. In order to then find the equation of the oblique asymptote, we'll carry out that division using either polynomial long division or synthetic division. And then the oblique asymptote is going to be the equation y is equal to just the quotient. So let's look at an example. Find the equation of the oblique asymptote, and let's notice that what we have here is an improper rational function because the degree of the top polynomial is greater than the degree of the bottom. Now, when that's the case, we need to divide to find the equation of the oblique asymptote. Remember, the top polynomial is the dividend and the bottom is the divisor. Since the divisor is linear, or a first-degree polynomial, we can actually use synthetic division. So let's do that. We start synthetic division with a backwards L box, and we put the 0 of the divisor in this box. The divisor is x minus 2. The x value that causes that to be 0 is 2, so the 0 of the divisor is 2. The coefficients of the quotient come out beside here, so we've got a leading coefficient of 1, 4 is the coefficient on x, and 1 is the constant. We're not missing any terms in that top quadratic, so we don't need any 0 placeholders. We'll draw a horizontal line, leaving a lane of space, and begin the synthetic division by bringing down the 1. 2 times 1 is 2, which comes under the next coefficient, and then we combine down. 4 combined with 2 is 6, and then we multiply on the diagonal to get 12, and that product comes under the next coefficient. And when we combine down now, we get 13. Notice this remainder is not equal to 0, which just means that the divisor does not divide in evenly. These are the coefficients of the quotient. Our quotient is going to be degree 1 because we started with a degree 2 dividend and we divided out a degree 1 divisor. That means that the quotient has to be degree 1. And the equation is going to be y is equal to 1 is the coefficient on x to the first power, and then 6 is going to be the constant. This quotient is going to be the equation of the oblique asymptote. Now, just a little bit of information as to why that is the case. When we divide an improper rational function, that can be rewritten in the form of quotient plus remainder over divisor. Essentially, we can think about this as being like an improper fraction, and then when we write it in this form, it's more like a mixed number. The quotient in this case turned out to be x plus 6. The remainder in this case was 13, and the divisor was x minus 2. So writing it in this mixed number format gives me an expression that is going to have the exact same graph as the improper rational function that we started with at the beginning. The oblique asymptote is going to be the line that the rational function begins to approach when x is getting infinitely large. Essentially, what is happening at the tails, which is similar to an argument that we had when we were discussing in behavior. Let's focus our attention on this piece right here. When x is infinitely large, the denominator of this fraction is infinitely large, while the numerator is staying fixed at 13. So the denominator is blowing up, but the numerator is super small by comparison. When x is infinitely large, this portion right here basically becomes insignificant. And the graph of our rational function begins to look more and more like just the equation of this line. So out at the tails, this rational function will be approaching the line y is equal to x plus 6, which is what we consider to be the oblique asymptote for this graph.